Swayam Prabha. Digital India. Educated India.
Welcome back to Mechanics and Control of Robotic Manipulator. In the last class, we have seen how to do a kinematic control starting from inverse differential kinematic. That is also we can call as a kinematic control because it's an open loop. So in this class, we are actually trying to see the kinematic control including inverse differential kinematic in a Matlab simulated form. So in the sense, whatever we have derived the equation, those things we are actually trying to do. So in the sense, you can see the inverse differential kinematics, both you can say joint space or you can say task space. So how one actually complement other, that we can see. So finally we will end up with a kinematic control. We will see joint scheme. So there we talk about computed velocity control, where we are computing the velocity in the form of kinematic control scheme. So where feed forward term and feedback term will be there. So even if we assume that the feed forward term is not there, so then we can consider as a proportional control. Then there would be a steady state error. Then the steady state error we can rectify with, so you can see proportional integral control. These all we have seen in the last class. So in this particular you can say lecture, we are trying to see that the same thing in Matlab. So for that we are actually taking a simple you call inverse differential kinematic model, which we have seen in the last class. So we would be assuming that the mu desired dot and mu desired are known. Then what we can actually see, so we need you can say the q dot. The q dot we can write as a j of you can say q desired inverse into mu desired dot, where this q desired can be obtained from the inverse kinematic. So in that sense we can actually do it. So even if the trajectory planner is giving straight away the joint space, so in the sense q dot desired and q dot, then that is actually straightforward, where the q dot can be written as q dot desired. So that's why that picture I have not plotted here. However, we can actually see in Matlab, so how we can do it. So for that we are actually saying the first one is in the joint space, where q dot can be considered as a q dot desired. This is the inverse differential kinematic model. So here we assume that it is straightforward. So where the desired is known and we are actually assuming that is the actual. So then we can actually write the Matlab code in this way. So since it's a differential equation, so we are trying to solve the q of time by numerically integrating. So again we will bring the Euler integration. So here actually you can see the 10 is the total duration of the trajectory. So or probably you can say simulation. So then the step size is here we have given as dt, and then the time span goes. So here I am doing only one addition because I am going to create a subfunction. In fact, last class itself I told we can use a subfunction. So anyhow I thought of actually introducing in this what you call kinematic control itself. So in the sense we are talking about global L1 and L2, where link length L1 and L2 I would be using in subfunctions also. So that's why we are actually taking it that way. So in that sense, what we are trying to do, the forward kinematic model we want to use it. So in the sense x and y we want to write it. So the x and y we can actually write it in this form. So the same thing I can write as one of the subfunction, where function x comma y, basically this particular function would be returning x and y for given theta 1 and theta 2. Okay. So even if you are actually going further and further, you can straight away write mu and you can say q. So that also we can do, where q of 1 would be related to theta 1 and q of 2 related to theta 2, and similarly mu of 1 is belongs to x, mu of 2 is belongs to y. That also we can use. Since this is actually beginning, so we will use independent variable. So the same way we want to know what is inverse kinematic model, because any of q desired we would be taking from the mu desired. So in that sense we need to know this. So we are taking an inverse kinematic model which we have derived in one of the you can say lecture. The same model we are taking it in Matlab function. So you can see this is going to return theta 1 and theta 2 for given x and y, right. So now these two functions are sufficient. So then we need to know Jacobian. So the Jacobian matrix we derived 2 cross 2 in the you can say the given form. The same thing we can write as a subfunction. So Jaco 2R is actually like Jacobian of the 2R serial manipulator. For given theta 1 and theta 2, the Jacobian matrix would be returned in this particular subfunction. So these are all the subfunction. So further what we want actually like trajectory, because so here we assume that the mu desired and mu desired dot would be there. So in that case, one of the easiest way is actually like we can take a cubic polynomial. So we are taking the third order polynomial or cubic polynomial. So we assume that Tf is given and T0 we have assumed as actually like 0. So in the sense general, we take x as the variable. So x of t I can derive based on this, you can say third order polynomial. So I can find the, you can say what you call the trajectory coefficients Tc for given input x naught, x dot naught, then xf, x dot of f, and Tf is given, then I can actually like find the trajectory coefficient based on this. Once I found the trajectory coefficient, what I can do, I can actually like go with x of t. So that is what we are trying to do here. So first case what we are trying to do, so only joint space, the q desired and q desired dot are given. So in that case, so we assume that the initial you can say position and final position of the end effector is given, and the time also given already Tf, okay, so which is 10 second. So now we assume that it's a 2R serial manipulator where L1 and L2 also given. So now what we can do, through the inverse kinematics we can find theta 1 initial and theta 2 initial. Similarly, theta 1 final and theta 2 final we can get. So further extent you want to find the initial velocities, so we can use Jacobian, because here we have like we know the end effector velocities. So in that sense we can find the joint space velocity by the, you can say, Jacobian matrix. So that is what we can actually like do it, right. So here actually like we take inverse Jacobian, so that anyhow in this particular case would not be that beneficial, okay. So that we can actually like correct it in the Matlab code. So what exactly we wanted. So then theta 1 dot, all those things we define, then we send it to the cubic you can say polynomial subfunction, then we will get the trajectory coefficient. So then we assume that initial conditions are actually like not equal to the same. So then you can actually like find the difference why we need kinematic control. So for that we assume that there is a, you can say 0.1 radian is the error in both cases. So then we are going for a numerical integration. There first we define the theta 1 of time, in the sense the desired we are trying to do. So theta 1 desired and theta 2 desired we have taken as this form. So then we are actually going with what you call, so q dot desired, so that also we can actually like derive it from here. So here there is no issue. So then we are actually like doing the inverse differential kinematic model, where so q dot as q dot desired. So then we are actually like making it this, and then we are actually like trying to find out the forward kinematic model, so that x desired and x we can actually like find. So then we can actually like plot it as a manipulator motion animation. So now we will actually like go to the Matlab. So we can actually like see, so the inverse differential kinematics for what you call joint space. So this we are actually like doing it here. So here I will just so correct it this. So this is one thing which, because mu is actually like mu dot equal to j of q into q dot. So in the sense we are actually like trying to find out q dot, so obviously inverse of this. So now these are the two things we have actually like modified. So now you can see like we have taken L1 and L2 are actually like 1 meter each or 1 unit each. So then the TF is actually 10 second. So the total simulation also like 10 second, that is what we have taken. So now this is the initial. So we are trying to do the inverse kinematic so that we can find theta 1 0 and theta 2 0. So based on that we have actually like found what you call trajectory coefficients. So if you don't want actually like straight away, for example you are giving theta 1 initial and final, you have joint space coordinate straight away. So then we can use this. So instead of using the you call inverse differential kinematics and inverse kinematics, we can directly use this. So let us go to the initial condition. Now we are taking as a open loop control, right. So theta 1 desired and theta 2 desired we have derived, and theta 1 dot desired and theta 2 dot desired also we have derived. And then we are using this inverse differential kinematic model, what it says. So q dot is actually like q dot desired. So we are trying to find out. So we assume that x and y are the actual, and x desired and y desired are the desired task space or end effector positions. So now we are actually trying to plot this. Okay, at the end we are trying to compare the results. Just I want to plot it. This is what we have used, and these are the sub functions which we have seen in the slide also. So now if I run this, okay, now if I run this, so I am using a shortcut F5. Okay, if I run this, so what you can see, like this is the desired, and you can see like the actual is different because it's a open loop control. It doesn't know like how to correct it. So in order to make it that clear, for example, the initial conditions are actually like same as the, you can say, desired initial conditions. So then you can see like this would be giving the same you can say trajectory following. You can actually like find it already, right. So this is what we can actually see. This particular plot is actually just for making more beneficial. So in fact this is not really required because we are trying to see whether the trajectory is following or not, right. So now I already said, so this is the case. So now we assume that the desired is actually like a 0, or you can say q dot desired is 0. So this will not even propagate. Okay. So in the sense I assume that this is actually like a 0, it actually like won't go. So in order to understand, this is the shortcut which I have used. So you can see it is not propagating. Why? Because we don't have any push, right. So that's why I said this inverse differential kinematic model, what you call open loop control, will work, or feed forward control will work when the q dot desired is non-zero and the initial conditions of both desired and actual are same. So that is what we have seen, right. So now you want to change this. For example, I am actually trying to change this probably, so 1. So I am just to change this. So you can see like it is trying to follow, right. So this is what we did in the joint space inverse differential kinematic. So the same thing we can do it even in the you can say task space. So there would be a small changes in the you can say code. So that is what we are trying to see here. So this is the task space. So now what change you can expect? So the theta 1 desired and theta 2 desired become x desired and y desired, right. So now theta 1 desired and theta 2 desired you want, then you can use inverse kinematics. So that is what we have done, and here mu desired and mu desired dot would be found. So this is what we have actually like get it. You can see mu desired and mu desired dot we have obtained. So then, so the q dot is inverse of, you can say, Jacobian multiply with mu dot desired. So this is what we have obtained, right. So the code, the you can say the prior of this and after this we are not going to change. So only this content is going to change. In fact, I want to actually like show it here. So this is the inverse differential kinematics of the task space. You can see like these segments are same and the input whatever we have taken is same. So only thing, the trajectory coefficients we are calculating for, you can say, x and y. So because of that the x desired and y desired we are getting. Similarly x desired dot and y desired dot we are getting. The same profile we have given, and here also like we have actually like given introduced this error. So you can actually like see that. So now, so you can see like the profile is actually straight line, right. So earlier it was not. So now if you are look at it this, you can see like it is non-zero, or you can say non-zero error I suppose to say, or you can say the desired you can say initial position and desired or actual initial positions are not same. So this is the desired initial position and this is the actual initial position, these two are same. So that is why the profile is not supposed to be followed here. So now in order to make it that, the condition what you have seen is this, right. If the velocity is non-zero and the initial, actual and desired are same, so then you will find that this would be a good control. That is why it is actually we call open loop control, because it is a feed forward, right. So there is no compensation for the actual case, right. So now even I introduce a small friction or some kind of uncertainty, this will not be following it. So that is what we want to actually like get it here. So we will go to the slide. So then we can see like how we can use this as a kinematic control. So for the kinematic control what we have taken, so one of the conditions we have taken that, so if the first order error dynamics is actually like going to be stable, So for that what we have taken, so lambda as the one of the positive constant we have considered. So then this is the what you call kinematic control model. So this is going to be a feed forward term which we have seen inverse differential kinematics. Now this is the feedback term, this is what we are going to call as a proportional control. So in that sense what code would be changing, so the initial thing all are same. So only thing we are adding the control parameter where we have seen the lambda, that lambda is coming here. So I have taken as 4, and further these all actually like same. So only added thing is the joint, you can say position error we have added, and you can see the you call the q dot change to q dot decide plus lambda into q tilde. The q tilde is actually q decide minus q. So now this is the change which we expected. So now based on that what we can actually like look at it. So the code would be actually like getting changed. So we can see like this is the so kinematic control we are actually like trying to see. So what we can see here, so these all actually like same whatever we have done earlier. So even we have end up with you can say the initial actual position is different from the desired position, and the lambda we have taken as 4. Okay, we will see if we change what will happen, and the joint position error is coming here and the kinematic control is changed here, right. So now if I run this, you can actually like see that even though the initial is actually like changed, but you can see like it is trying to follow it, right. So that is what we can actually like look at it. So if you look at the error, you can see initially it is 0.1 radian in both theta 1 and theta 2, that is actually like converged to 0, but it is having a small error. So that error actually like can be neglected by introducing some integral control and all, right. So now if I actually like increase this lambda or decrease my lambda, so what will happen, you can see like if I increase, so you can see like it is actually like much faster, and as well as you can see that the error would be eliminated very fast, right. You can see earlier it was going here, but now it is coming, and you can see error magnitude also very much reduced. So like that you can actually like take it. So instead of that lambda I consider as a 1. So then also you can see like the error would be taking, you can see like it is very significant, it is not followed, and the time taken for the error also converge. In fact it is not even converged, right. You can see if I by 10 second you can see some error is there, right. So these all what we have seen as a kinematic control. So what we have changed in the inverse differential kinematics, we have added the proportional control where you have taken error multiply with one of the positive constant, that is what we have done. So now we will go to the slide. So where we have considered only proportional control, in the sense you are actually like assuming that the q dot decide is unknown to us. Okay. So then what happened, the kp we have taken, and kp q tilde is the q dot. So in the sense what happened, the q dot decide will not be coming into a picture. So this would be having what we have seen in the last lecture, this would be having some steady state error. So that steady state error can be overcome with what you call the integral control. So where we have brought the integral control term, and then you can see like this is compensated with both the terms, right. So here we need to know the integral error. So initially we assume that the integral error ei equal to 0 0, then it would be propagate. So in order to understand this, we will go to again Matlab window. You can see this is the proportional control. Okay. So where you can see like kp equal to 4, and you can see like this is the same thing what we did, only thing the q dot decide is taken away, right. So now you can see like, so since this is actually like a cubic polynomial where q dot decide is there, but you have not considered. So you can actually like see that there would be a error which would be somewhat visible to us. So since it is actually like fast moving, you can see, so there is a error which is actually like significant, right. So this error you want to eliminate even without q dot decide. So then we can go with the integral error, or you can say integral error with the integral control. So this is what we can see. So now what we have added, so we have added, you can say ki into ei. So for that we have taken ei, ei is actually like ei of previous plus q tilde integrated. Okay. So in the sense this is the integral error. So now if I add ki some value, so here we have taken as 4. So if I added this, what you can see the same condition. So you can see like the error would be you can say reduced. So when t tends to infinity, it would be actually like C. So it is actually like reduced significantly, right? So you can see like earlier it was somewhere here, so now it is actually like reduced. Even if we increase Ki further, so then this would be converged somewhere closer. So if you want, we can actually like check it. So I am just putting probably 8 just for understanding, just to see whether that, you can see, right, it is already somewhat, it is faster, right. So that is what we can actually like look at it here. So you can see it is trying to converge to 0. So these are all the benefit of what you call proportional and proportional integral. So in that sense, you can actually see what is desired and what is actual, and then you can compensate. So let us move the final part where we are seeing the same thing, where the desired trajectory is given in the task space. So then we can do the computed velocity control, where the j of q inverse is coming. So this is one peculiar, because some cases the j of q can be probably infinity. So where, for example, in 2R serial manipulator, so if the theta 2 tends to be probably very close to 0 or 180 degree, or even 0 and 180, so this j of q inverse may be tends to infinity. So that is why we always avoid this kind of cases, but this is what the one additional input, where this control law we can actually like do it. So for that, what we are doing, so we are actually like taking one simple addition. Just for comparison, we are taking a q, so then we are taking a gamma, and you can see mu dot desired plus, you can say, gamma into mu tilde and inverse of jd, right. So this is what we have taken. In fact, instead of taking jd, even we can take j, so both will be the same result. Just to get that idea, we will go to the kinematic control in the task space. So we can see like this is the change which we were saying. So the mu tilde we calculate mu desired minus mu, okay. So then the q dot is actually like inverse of jd or inverse of j multiply with mu dot desired plus gamma into mu tilde, okay. So now again we see that the initial is having error, and this is the profile we want to follow, which is a straight line. We will see whether this is actually like following it or not, okay. So you can see like it is actually like following it, whereas in the simple inverse differential kinematics it was not followed, and you can see the error is actually like almost 0 in the mu tilde, in the sense x error and y error almost 0, right. So now even we want to check whether you want to use this only, you call q dot, sorry, j desired. It can be even actually like can be used j. So in that case, I will just take it. So this is actually like theta 1 and theta 2. So or I have to like use it. So I will just write j. So which means, so I will just see this. So I will just take it. This is just a j, which is from the q, okay. So this is, so q of 1 comma I comma q of 2 comma I, in the sense theta 1 and theta 2, okay. So now I calculated j, okay. So j I calculated, and then you can see like this is going to give. So now instead of this j, if I actually like do it, so the nature will not be changing, right. So that is what I wanted to show it here. So I hope now you are actually like clear what is kinematic control and what is, you can say, inverse differential kinematics, where we can use proportional control and where we can use proportional integral. And here also like we can actually like take it simple proportional in task space and proportional integral, these all same cases. So I hope you are actually like clear on the kinematic control and inverse differential kinematic of a serial manipulator. The next class we will see what is dynamic control, and in the dynamic control extension we will see the dual loop, where the outer loop we will be doing in a kinematic level and the inner loop would be in dynamic level. That is what we are going to see in upcoming lecture. So this lecture is on kinematic control with Matlab simulation. I hope you have enjoyed, and see you then. Thank you. Bye.